on to microgravity experiment design. So, ladies and gentlemen, there is one variable, and this is going to be a little more conceptually difficult, okay? And what I'm going to do is I'm going to tell you when a chunk of physics starts and ends, where once you hear this, you can extract that whole storyline and go right to microgravity experiment design. I'm not sure what I just said makes sense, but let's move through this. So, ladies and gentlemen, there is one variable that plays a critical role in virtually anything we want to study, whether it's physical, chemical, or biological, but it's often taken for granted. Cindy, would you like to tell me what that variable might be?
Gravity.
Gravity. Gravity is everywhere, and it plays a critical role in virtually anything I want to study, but it's taken for granted. What do you do with gravity? Well, here's actually two examples, okay? The first is, even a germinating seed knows about gravity, because when it germinates, the roots go down, the shoots go up. It's called geotropism. Your body knows about gravity in myriad ways. I'll give you one example. Every time you take a step, your bones are compressed under your own weight. And it sends a bioelectrical feedback to the body saying, hey, keep making those bones. Bones are good. We need those bones. But in a weightless environment, the astronauts have no bone compression because they are apparently weightless, which means the signal coming back to the body is, we don't need the skeleton anymore. And they start excreting their skeleton. They start excreting their bones. And astronauts have to work with compression, with pulleys and springs to compress their bones to minimize bone decalcification. Gravity is everywhere. Biology, virtually all biology, gravity plays a critical role in virtually all biology, in chemical systems, in physical systems. So here is the flavor of question that drives microgravity experiment design. Okay, here's the secret sauce. The flavor of question is, what is the role of gravity in that or this or that thing down there? What is the role of gravity in something? Now, if I want to understand, if that's the essential question, and I told you essential questions scream what the independent variable is, right? If I want to understand the role of gravity in something, what do I need to change? What needs to be the independent variable that I change?
The amount of gravity.
The amount of
Gravity.
Gravity. Well, here's the problem, ladies and gentlemen. I can't change gravity. I can change the light level, I can change humidity, I can change temperature. I can't change gravity. Can't do it. Let me explain why, okay? So let me say that we know that any two masses in the universe will attract each other with a force of gravity. But it's a very weak force. You don't see these two coffee cups flying into each other. It's an incredibly weak force. And so for you to see gravity easily, if you want to see gravity easily, at least one of those two masses has to be really massive. So my question to you is, can you give me an example of two masses where the resulting gravity is something that you get to experience every second of every day in your lives? Give me an example of two masses where one is massive and it gives rise to a gravity that you experience every day of your lives, every second of every day.
Like the Earth?
The Earth and?
The Moon?
Well, do you experience the Earth? And I mean, you know, you've heard about the tides, but I want something more personal. Two masses, one is massive, and in fact, right now, you're depending on the gravity in this example of two masses for us to have our video conference because you're not floating out of your chair. So what are the two masses that I'm talking about as an example?
The sun.
Anybody? No, the sun.
The Earth
The
and the
sun
sun?
does not play a role on you sitting in your chair right now.
Is it Earth and ourselves? Is that what
Yes,
you're looking for?
Earth and you. Earth and you. One of the masses is massive. It's a big sphere, 8,000 miles across. And right now, all of planet Earth is pulling down on you. I'm not just talking about the part of Earth under your feet. All of the continents, all the mountains, the oceans, the crust, the core, the mantle, all of the mass of planet Earth, a massive rocky ball, 8,000 miles across, is pulling down on you right now. And the force of gravity exerted by the Earth on you is called your
Wait,
weight. When you get on a bathroom scale, what you're seeing is the force of gravity exerted by all of Earth on you pulling down. And it must be kind of a weak force because if you weigh, say, 150 pounds, right? It took the entire mass of planet Earth to pull down on you with a force of 150 pounds. Is everybody with me on that? Okay, so now I need to change gravity to do my experiment. Well, what do you think happens when I move farther from a gravitating object? In other words, if I move two masses farther apart from each other, what happens to the force of gravity between them?
it decreases.
That's kind of intuitive, right? The farther away they are, the less they know about each other, and so sort of gravity gets weakened, right? So, what do you think might be a way to do this experiment?
Going into outer space.
Going into outer space. Okay, cool. So here's so now you got to follow me here. All right, you ready? You ready? Hey, buckle up. You ready? I don't know. I'm seeing a lot of uneasy faces here. Okay, so what's the tallest mountain on Earth?
Mount Everest.
Mount
Mount Everest. Mount Everest. Not tall enough. I need to find me a mountain 47 times higher than Mount Everest. 47 times higher. Well, that's a way cool mountain because when I walk to the summit of that mountain, I'm 250 miles above the surface of the Earth. What do you think I might find 250 miles above the surface of the Earth?
Is it the ISS?
The International Space Station. It orbits 250 miles above the surface of the Earth. So I'm at the same distance from the Earth as the astronauts, right? I'm at the same location. I can see the International Space Station fly right by my face. I look in the big window called the cupola and they're floating around over there. What do we call, have you seen astronauts, a video of astronauts in space? In the International Space Station or the shuttle, what do you notice? What do you see? Describe to me what you're seeing.
They're floating.
They're floating around, and we call that experience what?
Zero gravity.
Zero gravity, or it's a W word.
Weightless.
Weightlessness. It's as if gravity is turned completely off. It's as if there's no gravity. There's no up, there's no down. They're floating around. It's you said zero gravity. Yeah, that's what it is. That's what weightlessness is. So here's my deal, okay? I go to the top of my mountain, 250 miles above the surface of the Earth. And by the way, I brought my trusty bathroom scale with me. And I put it down on the top of this mountain, and the astronauts just flew right by my face, and they're floating around in the International Space Station. And I step down on my bathroom scale, and what do I weigh?
Yeah.
You might say zero, because I'm at the same distance as the astronauts, and they're floating around like they're weightless, like there's no gravity. What's another possibility?
Close to weightless, like barely anything.
Close to weightless. Well, here's the deal. Another deal. I have lots of deals. I stand on my bathroom scale and I weigh almost the same as what I weigh on the surface of the earth. 90% of what I weigh on the surface of the earth, almost the same. Let's understand that. Here's the earth. What was the diameter of this planet?
8,000 miles.
8,000 miles. How far above the earth is the International Space Station?
250 miles.
250 miles. So is this International Space Station out here? This is 8,000 miles across. The International Space Station is 250 miles above the surface of the earth. Where do I put it? Yeah. Is that Morgan? Morgan says like right here. Right there. It's barely above the atmosphere. The atmosphere is really thin. You might think that you're living under an ocean of air, but the atmosphere compared to Earth is thinner than the skin of an apple compared to an apple. Let that sink in. We destroy the atmosphere, we destroy life on Earth. My plug for climate change. So the International Space Station is just skimming the surface of the Earth. Have they moved very far from the Earth? So what do you think the force of gravity exerted by Earth on them is? It's almost the same as on the surface of the Earth because they've hardly moved from the Earth. Does this explain why I still weigh 90% of what I weigh on the surface of the Earth when I stand on my bathroom scale? Yes? No? When I'm on my mountain 250 miles above the surface of the Earth, same distance as the astronauts above the surface of the Earth, I weigh 90% of what I weigh on my scale in my bathroom on the surface of the Earth. Does that make sense? Why does that make sense? Because I've hardly moved away from the surface of the Earth. But the astronauts are at the same distance from the Earth as I am on top of my mountain, which means the force of gravity exerted by Earth on them, their weight, is 90% of what they weigh on the surface of the Earth. They cannot be weightless. Anybody who thinks that gravity disappears in outer space is dealing with a really deep misconception. Gravity is alive and well, and skimming the atmosphere, the top of the atmosphere, the force of gravity exerted on you is almost the same as exerted on the surface of the Earth. So what's the problem, ladies and gentlemen? What's the problem here?
They're in orbit.
Oh, no, that's not the problem. That's the solution. What's the problem? Come on. Just say what you think.
The Earth is spinning.
No. What?
No.
Okay. So what does it seem? What does it seem like they're experiencing?
Weightlessness.
No gravity at all.
Falling.
No gravity at all. And right outside their window, I'm standing on a mountain and I'm seeing that I weigh almost the same as what I weighed on the surface of the Earth. There is a disconnect between those two things. So to understand what's going on here, we have to go to my favorite town because I was born and raised there, New York City. And my favorite building is the Empire State Building. And you can take an elevator from the ground floor up to the 104th floor. There are no windows in the elevator. And I bring my trusty bathroom scale with me into this elevator. And I stopped at a kindergarten class before I went over to the Empire State Building, and I grabbed one of their chairs. And what's cool about that chair is that when I stand on it, I'm a foot above the floor. It's a tiny little chair. Okay, now let me ask this. Is the Empire State Building a big structure? How does it compare to Mount Everest? Tiny. Tiny structure. How does it compare to a mountain 47 times higher than Mount Everest?
Very, very small.
Really, really small. So if I am on the 104th floor of the Empire State Building, for all intent and purpose, am I on the surface of the Earth? The Empire State Building is a tiny little insignificant thing that humans built. Okay. So now I take the elevator to the 104th floor. The elevator stops, the doors open up. It's as if the elevator is part of the 104th floor. I see people walking around at the observation deck. And now I do my experiment. I get up on my chair and I step down 1 foot onto the floor to where the bathroom scale is. And what do I weigh?
The same.
The same as what I weigh in my bathroom on the surface of the earth, because the Empire State Building is a tiny little thing. Now I'm going to do the experiment over again because scientists have to look for reproducibility. So I get back up on my chair, and what I don't know behind me is the doors just closed. And the moment I'm walking off my chair, somebody does something really bad, cuts the cable holding the elevator. What happens to the elevator, me, the bathroom scale, and the chair?
It pulls you down.
We start to fall. What's causing all of those things to fall?
Gravity.
Gravity. What do we call the force of gravity exerted by Earth on the elevator?
Its weight.
The elevator's weight. So the elevator is falling under its own weight. Now, can somebody tell me what's happening to the speed of me, the bathroom scale, the chair, and the elevator car?
You're accelerating.
I'm accelerating. What does that mean?
You continue moving faster.
Okay, so I'm starting from rest, the cable is cut, and I start moving faster and faster and faster because there's a force of gravity pulling me down, causing an acceleration. We call that the acceleration due to gravity. Does anybody have a number memorized for the acceleration due to gravity? Because we like to memorize this number.
9.81 meters per second squared.
Okay, so Morgan said 9.81 meters per second. What is it? 9.81 what?
Meters per second squared.
Okay, what does that mean, Morgan? Tell me you know more than it's memorized. Tell me what it means.
You're go-
Aha. Okay. It means
It's
that
acceleration due to gravity.
it's the acceleration due to gravity, but 9.8 meters per second means that every second you're moving 9.8 meters per second faster. That's what an acceleration is. Okay. But I don't know what 9.8 meters per second even looks like. It's a unit I don't know. So I'll build a bridge to the familiar for you. You all drive around in cars, you take public transportation, you know what miles per hour is, right? The acceleration due to gravity means that every second you increase your speed by 20 miles an hour. Every second you increase your speed by 20 miles an hour. Can somebody tell me how fast you would be moving after 1 second after the cable was cut?
20 miles per hour.
20 miles an hour. After 10 seconds after the cable's cut, how fast are you moving?
200.
200 miles an hour. After 100 seconds, if the elevator shaft is long enough and you don't go splat, okay, after 200 seconds, how fast will you, I'm sorry, after 100 seconds, how fast will you be moving? 2,000 miles an hour. The acceleration due to gravity is huge. And I don't know what 9.8 meters per second means, but I understand what increasing my speed 20 miles an hour every second means. That's huge. So now, let me ask a question. What's inside the elevator shaft?
The chair, the weight, and yourself.
No. What's below the elevator car inside the shaft?
Air.
Air. And what will the air do?
Slow your fall.
Slow your fall. It's called air
Resistance.
or air drag. And so let me give you an example. I decide I want to go parachuting. I jump out of a plane. For the first few seconds, I'm accelerating due to the acceleration due to gravity. But the air under me is pushing back. And the air resistance is dependent on how fast I'm moving. The faster I move, the bigger the resistance, which means that as I continue to go down, my acceleration goes to 0. I reach a point where I can't go any faster because the air won't let me. Does anybody know what we call that?
Terminal velocity.
Terminal velocity. And for a human being, it's about 100 miles an hour. Well, hey, if you go splat at 100 miles an hour on the ground, you're not going to live to parachute another day. So the solution is you open up a parachute, which increases the drag tremendously, which slows you down so you can land and parachute another day. Everybody understand that concept? Okay, so what I'm going to do is I'm going to take all the air out of the elevator's shaft. And as the car is going down, I want to make sure that there's no rubbing of the car on the shaft walls. There's no friction. And so if that's the case, when the cable is cut, there's no air resistance, there's no frictional force rubbing up against the elevator shaft. Once the cable is cut, what's the only force acting on the elevator? And me and the bathroom scale in the chair. What's the only force acting on us?
Gravity.
Gravity. And what do we call the kind of falling when the only force acting on an object is gravity?
Is it free fall?
Free fall, because it is falling free of any other forces. And so now will I keep accelerating if there's no air drag and no friction? Will I keep accelerating? Absolutely. Now, here's my question. Will the bathroom scale, the chair, me, and the elevator car all accelerate together? Will they all come down together? How many people say yes? Thumbs up. How many people say, I'm not sure, you got to give me more? Okay, so here's the deal. You can go on YouTube and you can go and search out an Apollo astronaut feather and hammer. There's an Apollo astronaut that brought a hammer and a feather to the surface of the moon, and from the same height, dropped the feather and the hammer at the same time, and both of them hit the moon's surface at exactly the same time. He proved Newtonian mechanics, that Newton was right. The acceleration has nothing to do with the mass. If I'm a big guy and I drop a Toyota Camry and a rock from the same height, a tiny rock, a pebble from the same height, in an airless environment, they will hit the ground at the same time, because let me remind you, the acceleration due to gravity that we talked about before, 9.8 meters per second squared, or 20 miles per hour increase every second, has no mass in it. It's mass independent. Everybody with me on this? Okay, so here's the deal. The doors close, I'm on my chair. The second I walk off my chair, somebody cuts the cable and everything starts accelerating down. Here's the secret sauce. If I move down in a certain period of time, let's say in 10 seconds, I move down, I don't know, 100 feet. Okay, I'm accelerating down. In 10 seconds, I move down 100 feet. Will the elevator's floor in 10 seconds also move down 100 feet? Let me say it again. If we're all accelerating down together, if I move down 100 feet in 10 seconds, will the elevator's floor move down 100 feet in 10 seconds? Yes. Can I catch the floor? Where was I when the cable was cut?
On the chair.
I was actually just off the chair. I stepped off the chair. And how far above the elevator's floor is the chair?
A foot.
A foot. So when the cable is cut, if I move down 100 feet in 10 seconds, will the elevator's floor move down 100 feet in 10 seconds also?
Yes.
Can I catch the floor?
No.
What do I see?
Floor is
Explain
moving
to me
down at
what
the-
I'm experiencing in this elevator.
You're seeing that you're not falling, and you're seeing that you're weightless.
I'm floating a foot above the floor. I have to be floating a foot above the floor. Now, this is really weird, right? I mean, it sounds kind of crazy, but that's the way the world works. If I go down a certain distance, the floor moves. If I go down a certain distance towards the floor in a certain period of time, the floor moves away from me the same distance in the same amount of time. I can't catch the floor. All I know is when I did the experiment the first time, I stepped down on the bathroom scale and I weighed the same as what I weigh on the surface of the earth. I do the experiment over again and I look around and I say, who turned off gravity? There's no gravity in this elevator. Somebody turned off gravity. I could push off this wall and float over here. I can push off the floor and float to the ceiling. And do I see the different floors of the Empire State Building flying by at an ever-increasing speed? Do I see the floors of the Empire State Building? Why?
You're still in the elevator?
I'm in the elevator and there's no
Window.
No window.
There's no windows. There's no windows. I'm in the same elevator. All I know is I did the experiment over again, and now I'm floating and there's no gravity. I'm weightless. And here's the irony, ladies and gentlemen. It is the force of gravity exerted by this that's causing me, the bathroom scale, the chair, and the elevator to plummet at an ever-increasing speed. But inside a freely falling laboratory, everything will behave as if gravity is turned completely off. Does everybody understand? I know I pulled the rug out from under you and now we're kind of building a brave new world, but does everybody understand the concept behind this? And by the way, it's all on the website. I wrote it. I know it's on the website, okay? So now here's the deal. You don't know that I'm kind of like an alien from another planet because there's no air in my room and I'm just kind of sending my thoughts to you. It looks like I'm talking and there's sound traveling, propagating to the microphone. That's not true. There's no air in this room. So if I drop this ping pong ball, is it in free fall if there's no air in this room? Right? The only force acting on it is gravity. So, ladies and gentlemen, is this the elevator? Yeah. Now, if I push on this, I give it a little force, I push on it. And so I've accelerated from it being at rest to a little speed when it leaves my fingers, right? Once it leaves my fingers, is it in free fall? If I go like this, if there's no air in this room, is it in free fall? Once it leaves my fingers, the only force acting on that ball is gravity pulling down. Can somebody explain to me the path it takes when I throw it a little bit?
Parabolic.
Yeah, so it follows a path, a parabolic path, but okay, it follows a path and it hits the earth. What if I throw it a little faster? Once it leaves my fingers, what's the path?
You give extra acceleration for it to be after released, but it still free falls.
So I'm saying that again?
You just give an extra acceleration to the ping pong, but
Yes, exactly. So, but it still free falls. But now tell me how the path has changed if I throw it faster.
The X increases.
Yeah, X increases, so it goes farther before it hits the ground. If I keep throwing it faster and faster and faster, it goes farther and farther out until it hits the ground. Until if I throw it really, really, really fast, as it arcs due to gravity, it will swallow all of planet Earth. And in fact, in 90 minutes, I can catch it from the other side. And so if there's no air resistance, if I throw this really, really fast from my desk in that direction, as it arches, it will swallow all of planet Earth and come back in 90 minutes, and I can catch it in my hand. So this is the elevator. This is the International Space Station. The International Space Station is in free fall. It's in continuous free fall. And anything in a freely falling laboratory will behave as if gravity is turned completely off. The astronauts are in that elevator. And the force of gravity exerted on the astronauts and the International Space Station, their weight is what's causing them to freely fall in a circular orbit around the Earth, as opposed to just flying off into deep space. Does everybody understand this storyline?
Yes.
Okay, so again, the idea is that we want to understand the role of gravity in something, and we have to change gravity, but we can't go far enough from Earth where gravity diminishes enough for a change in gravity, because just going to the International Space Station costs $55 million per astronaut. And they're just skimming the surface of the Earth. So can anybody explain to me how we could do a microgravity experiment? A microgravity experiment is an experiment in a weightless environment. How do we do a microgravity experiment?
The ISS is in orbit, so it's in continuous free fall.
So if you bring your experiment to the International Space Station, it will behave as if gravity's turned completely off, at least according to the experiment. What else do we need? Charlie, you talked about this before.
Control group, that's still
We need a control experiment operated where at the same time?
on the surface of Earth.
On Earth, in gravity. According to the experiment, this one operated in the seeming absence of gravity. This one operated in gravity. And when you bring the flight experiment down and you put them side by side, according to the experiment, you changed gravity. And you look for behavioral differences in what you're studying to understand the role of gravity in that. Does everybody understand how simple a microgravity experiment is? Okay, so the deal is, I talked about the force of gravity exerted between two objects, and we looked at that, and we looked at an example of you and Earth, and the fact that the Earth is pulling down on you with all of its mass to give you which yields your weight. And we talked about the fact that two objects moving farther away, intuitively you think gravity diminishes. And so I said, well, how do you think you do a microgravity experiment? He said, well, move it far from the Earth. But then we realized the International Space Station is not far from the Earth. Gravity hasn't diminished much at all, only down 10%. So you can't move it into space far enough away where gravity diminishes. But then we went and we looked at the elevator and continuous free fall, and the fact that inside a freely falling laboratory, everything will behave as if gravity's turned completely off. And then I showed you the International Space Station is the elevator. It just had a very large horizontal velocity, initial velocity to keep it in motion. So all of that stuff, from gravity between two masses all the way to the International Space Station is in free fall. Once you understand that storyline, so you understand the physics behind it, you can kind of forget about it. Because fundamentally, a microgravity experiment design is about tricking the experiment into thinking there's no gravity and running a control experiment on the ground at the same time. Does everybody understand where we are with this? Any questions?